LetUsTalkIT webinar series. And we are extremely excited to have you all. Those who have joined us on YouTube, Facebook, we welcome you as well. And this is an important topic, and we think that I'll just give a small introduction, and then we can get started. And so today's topic, we have an introduction to quantum computing. So scientists are looking at quantum computing that could potentially transform our businesses and societies. And this webinar would help you to understand quantum computing, which is a fundamentally different way of computation. And if you want, then you can learn and join this webinar and learn to explore, define, and benefit from the rapidly approaching age of quantum computing. And also to present this session, we have a very special guest speaker today. He has been one of our guest speakers earlier, in last year. And we are extremely excited and honored to have him back with us. And he likes to put extra feathers on his hat and then come to us. Previously, he presented a topic, ABC of AI. And then when I asked him, what are your passions and everything? So he said, you know what, I love flying, and I have a sports pilot license too. And so this time he is working as a customer engineer, SME solution architect for artificial intelligence, machine learning, data and analytics at Google. He joined this, Google recently. And he's leading a team of data scientists in using data science, machine learning, and deep learning to drive product innovations, customer success, and marketing optimization. And the added feather to his cap is that he has already written a book. He is an author now. He's the author of the book, Adopting TensorFlow for Real-World AI, a Practical Approach, TensorFlow version 2.2. Now, we are extremely honored, Naresh, to have you here. Over to you.
Thank you, Julian. So hello, everybody. As Julian said, I'm Naresh Jasutani, and I work at Google, Specialist Customer Engineer for AI, ML, and data analytics space. So in this session today, I just wanted to set up the expectation. You would learn what is quantum computing and what is and why is it different from the classical computing. And then we are going to talk about the use cases of quantum computing and what are some quantum processors already available for us. And then you might have a question that, how do I get access? How do I get my hands on to quantum computers or quantum processors? Is it possible? Is it going to be too expensive? The answer is you can get access to the quantum computing processors at no cost, and I'll show you how. So let's get started. So first of all, what is quantum processor and how is it looking like? Now, when the classical computers were launched back in mid-1900s, people thought that, oh, it's going to change everything and it's going to be, the future. And obviously it was. Today, quantum computer is at the same stage as classical computers were almost 80 years ago. Now, Google has claimed to have achieved quantum supremacy using some processors like Sycamore, which has 54 qubits. I know when you hear qubits, it's a new term. Qubits are analogous to classical computing bits, as we know, zeros and ones. 54, the number itself, may not sound big, but this is one of the most fastest and one of the fastest computers in quantum processors in quantum world. You have another processor which is being built by Google, Bristlecone, with 72-bit qubits. What is a qubit? Again, it's analogous to bits, quantum bits. We call it as qubits. Just to give you an understanding of how a quantum processor looks like, it's on the right side here. This is a photograph of Sycamore computers. processing quantum computer, and you see it's very complex. We're going to talk about this a little bit as well. To understand how fast these computers are, in 2009, Google put an experiment on these processors, which completed a task in 200 seconds, which is just over 3.5 minutes. Had it been a classical supercomputer, to think of any supercomputer you might know or have thought about, it would take that computer 10,000 years to finish. So that is the difference. 3 minutes to 10,000 years. Why is it so different? Good question. Let's give the answer. So quantum bits provide exponentially more computing power for any computer which is running on quantum. With 54 qubits is equivalent to 2 raised to 54 classical bits. In other words, the number of classical bits which would be required to represent a 54 qubits sycamore processor is 2 raised to 54, exponentially higher. It must be in billions, trillions, and even more. How these quantum computers are built. And I'm going to talk about these qubits and everything in a few minutes. So, and these are some details on how these chips and processors are created. You don't have to know this, but it's good to have that knowledge. The first step to build a quantum computer or processor is to use a superconducting material. That means zero electrical loss. The wiring you see around you today has losses, but a superconductor element, metal, will not have any loss, near zero loss. And how do you create those type of superconductor materials? By using temperatures less than 50 millikelvin, absolute zero. I'm not talking about 0 Fahrenheit or 0 degrees Celsius. I'm talking about absolute zero, at which all the atoms are in a rest state. There is no movement at all. The cold temperatures are, and the vacuum is created inside the chirostat, which helps to create a qubit environment. In this diagram, the warmer stages are on the top, while at the bottom here, during the at the end, like the bottom of the processor, they are really sub-zero temperatures, like absolute zero temperatures. So that's how a quantum bit is created. Quantum computer is created. The bits, qubits, are the processing functions or processing bits in quantum computing. Let's talk about what are the use cases, and then we'll try to understand qubits. They are a little complicated. So use cases of quantum computing. The fundamental idea of the quantum computing is to break through the barriers what you have for classical computers today. A classical computer can easily be hit the ceiling if you want to do a factorial, and when you do a factorial, it hits a ceiling at some point in time. That is not too much. But a quantum computer, you can go on and on and on and on. Various use cases of quantum computing include, but are not limited to, cryptography, security. The most modern secured devices or security protocols are broken by quantum computing. So those are not even secured once you talk about quantum computing. Medicines and materials, machine learning and big data. Let's talk about some industry specific in farming. When you create a fertilizer for a certain kind of plants or nitrogen component, it's very difficult and expensive to put a fertilizer, a composition of fertilizer together. And that is where quantum computing can help, because quantum, the word itself, means a finite amount of energy. We're going to look at that in a few minutes. Healthcare, like COVID-19 data, COVID-19 molecules. To create a drug of COVID-19, people have used extensively quantum computing. They still haven't got the answer yet. There are a few drugs which are at some stage of testing, but we do not have the answer. But quantum computing is known to help industries like healthcare to find out the right combination of molecular formula for any drug going forward. We are not there yet. And other use cases are like smart cities to find out traffic optimization, as well as finding out materials for electrical vehicles. Combating global warming. The number of processors and CPUs being used today, you talk about cloud technologies, and even your machines and cell phones, they are generating a lot of carbon footprint. In order to avoid that and minimize it, that is where quantum computing can help, because it's going to be doing work where millions of computers today may not be required. It can work to that level. Now the question is, will the classical computers that exist today cease to exist once quantum computing takes over? Probably not. Somebody told me a very interesting thing. You have pictures and you have captions. Think of pictures as quantum computers and captions as classical computers. If you have pictures and captions, they complement each other. You cannot replace a picture by a caption or a caption by a picture. So quantum computing and classical computing are being envisioned to be complementary to each other rather than overlapping or replacement of one another. So it's a good thing coming in future when you have quantum computing for high quality and heavy workloads, and then classical computer, of course, it will evolve over a period of time. So we have seen, quantum computers use cases. Let's focus on understanding what is a qubit, what is a quantum computer. So I always give this example, and you will find this example at a lot of places, a flip of a coin. So if you and I have to do a coin flip to find out whether it's going to be heads or a tails, I'm going to flip a coin, wait for the coin to be at rest, and then see who wins the toss. Now imagine a situation wherein the coin is still in the air, it's not at rest. It goes through a series of heads, tails, heads, and tails before it comes to rest. What if we can decide who wins the toss by the first flip? So it's still in the air, it's not even coming down. You have tossed the coin, and if you have that sub-millisecond vision, we'll find out who wins the toss. You don't have to even wait for the coins to come to the rest. That is the basic difference between a classical computing and a quantum computing. For classical computing, it waits till the coin comes to rest. But quantum computing can do a lot of calculations. Now, if you look at a coin, at a state, it is heads, another state, it's a tails. But classical computing, it can be either heads or tails. Let me talk to you again on this concept. So this is your heads, this is your tails. So when a coin is flipped over a time axis, you would have heads, and tails before it comes to rest. Each of these positions, that means when the coin is flipping, and I ask you to measure, you would say, oh, sometimes it's heads, sometimes it's tails. It depends on what moment, which position you measure. And that position is known as superposition. A superposition is a special mixture of the quantum bits, qubits. This coin, in this case, is a qubit. It's a special mixture of the quantum energies in such a way that you measure it to be a heads or you measure it to be a tails. But remember, at the qubit itself, the coin itself, before it comes to rest, can be 1 or 0 at the same time. I know it's complex. Let it be. Otherwise, everybody would learn quantum computing, right? I'm just kidding. Let's move on. So let's understand a little deeper what is quantum computing and understand this. We started looking at the processor, then we looked at the use cases. We looked at an analogous real-time example of a coin flip, which is being used to explain the concept of quantum computing, but this is the scientific explanation. The word quantum itself refers to discrete quantity of energies. That means energies in the real world comes in forms of packets, defined quantum of energy, quantities of energies. Let's take a look at a photon. A photon moves or travels, and that is, it requires an energy to travel. The finite amount of energy required for a photon to travel is a quantum energy. Let's look at an example of nucleus and an electron. Let's assume that this is the lower orbit, 0 orbit, and the outer is the orbit number 1. Let's consider this state as 0 and 1. Please note that this is the representation of a quantum bit, qubit. So pipe number 0 and this represents a state of quantum 0, and this represents a state 1 of quantum. Now, if you supply a finite energy to this electron, it moves from a lower orbit 0 to the higher orbit 1. There can be just two orbits, 0 or 1. It cannot be anything else. But that energy, if we can control that energy, we can create a quantum computer. If we can control the gates, the gate is the logical function which provides a computational signal to the computer processor. You don't have even to see that. It's just a concept. A superposition of this electron, that superposition means the position at which you measure. Remember the coin flip? Heads, and tails. So the superposition is denoted by C0 of this quantum bit plus C1 of this quantum bit. If C0 is, if the electron is here, then C0 will be 1 and C1 will be 0. If the electron is here, then it will be the other way around. So a combination of this equation can tell you, based on the values of C0 and C1, which are complex constants, can tell you where the electron is. And that is the concept of quantum computing. I know it can be a little very scientific. Let me try to break it down in the computing language. So 0 is a state of qubit 0, quantum bit zeros, and 1 is a state of quantum bit 1. Now, if you have a classical bit, let's assume you have 3 bits, B1, B2, and B3, with the states 1, 0, 1. It cannot have any other state. If you measure B1, it will be 1 always, unless and until you change it. B2, 0 always, and B3, 0 always. Sorry, 1 always, unless and until you change it. However, that's classical computing. In quantum world, if you have a qubit represented by QB, at the same time, it will be 0 or 1. It will be constantly changing. It depends on the position, superposition you measure it. The instant or instance of time you measure it. The position you measure it. The superposition of qubit is defined by a function, a formula, known as C0 of 0, as we seen earlier, plus C1 and 1. So take an example of 1 qubit. One qubit is defined as C0 of 0 and C1 of 1. That means to represent one single qubit, you would need two classical bits, right? For defining 0 or 1, 1 or 0. For two qubits, that's the calculation. You would need 4. So if you look at it, the number of qubits are exponentially increasing. 2 raised to the power 1, 2 raised to the power 2. And that is where we saw earlier the number of classical bits B required to represent the quantum bits is 2 raised to the power. So imagine Sycamore quantum processor, 54 qubits, 2 raised to the power of 54. That is why that formula. I know it can be a little bit confusing, but it's okay because you are getting into the quantum world. Let's move on. What is a quantum circuit? Oh my God, another term. Don't worry, I have a video specifically defining the terms, the commonly used terms in the quantum world. So what is a quantum circuit? Let's take a qubit. Remember the coin? Those were the flips. Now, before the coin comes to rest, you can apply a finite quantum of energies via logical computation known as gates. And these represent gates, K0, K1, K2, and K3. So if you have 3 qubits, you will represent it like this. And this is your state of rest. These are quantum gates. On a time axis, here, remember the flip of the coin? On a time axis, these are quantum gates. And you can apply, these are gates. This diagram is a blueprint for quantum computation. So I repeat one more time, a quantum circuit is a diagram which is read from top to bottom and from left to right on the time axis. So quantum circuit is a representation of quantum bits on a time scale with gates applied. And these gates could be of multiple types, like H gate, RX gate, Y gate. There are a lot of gates, which is out of scope of our discussion today. We're going to discuss gates at some other point. This is how you would do a computational quantum computation based on the quantum circuit. I will show you in the demo today how to use TensorFlow, which is my favorite package in Python, and do quantum computing today. You don't have to buy any quantum processor, nothing. It's available for you to use. So let's see some of the terms used for quantum computing, commonly used terms. Quantum, as we discussed, refers to a discrete finite amount of energy. The energy which can change the electron's position from a lower orbit to the higher orbit. The energy which can push a coin from one flip to the other. The energy levels, the finite energy level, is something which is being controlled in quantum computing. Qubit. Qubit is analogous to bits in classical computing, known as quantum bits or qubits. Again, the number of classical bits required for quantum computing is 2 raised to the power of number of qubits. So imagine Sycamore computer, 54 bits. Bristlecone computers, 72 qubits. It's massive. Superposition. It's a special mixture of energy levels of 0 and 1 with the weights C0 and C1. to tell you the position of a qubit. Superposition is that position where you do the measurement. That means the coin is flipping. I would say let's measure when the coin has flipped 7 times or 8 times. That is point in time. The coin is not at rest yet. Measurement. When you talk about superposition, you will talk about measurement. Measurement is a step where you measure. That means the qubits, quantum bits, is converted to a classical bit. Quantum gates, as we discussed, these are instructions to send control signals in quantum. A packet of control signals are being sent, and gates perform that logical operation instruction on the qubit. I know it's a very low level detail. Probably nobody, or you might not have even learned about this in a classical computing. In classical computing also, you have control signals, gates, transistors. Remember the PNP junctions and the NPN junctions? This is one of those. Quantum circuits. The quantum circuit is a diagram which you saw the last time, wherein you have quantum bits on the left, you have time series, and you have gates applied, describing how to perform a quantum computation. Again, a quantum computer is that computer which uses quantum processor, and it acts and store information in quantum form. Again, when I say quantum form, I mean quantum bits or qubits. NISQ. This is a very new term. NISQ full form is Noisy Intermediate Scale Quantum. That means the scientists of today's world, are really intelligent, smarter than the previous, obviously because you have that learnings coming in. They define this embryonic stage of quantum computers we are in today as NISQ, a NISQ era. In future, they feel that the quantum computers will be really powerful and that era will be called something else, but today it's NISQ. This current era is a NISQ era. And then let's talk about, so these were all science thing, right? Scientists, I'm not too sure these were very, very complex things for me to understand at the first go. I understand that. But let's put quantum computing in practice. In order to do that, you would use TensorFlow quantum computing. This is my favorite to use quantum computing. So TensorFlow quantum is a Python framework. So you would need to know Python. And I have some series of videos which I can share with you to learn Python. So TensorFlow quantum is a Python framework for quantum machine learning. TensorFlow quantum can be used and is available for you to use for ML applications and all other applications using Google quantum computers. I'm going to show you how can you access that. Cirq. It's an open source framework for quantum computing. So in order to do quantum processing, you would use a framework, which is again Python based, known as Cirq, CIRQ. Now, TensorFlow quantum implements the components that are needed to integrate with TensorFlow and quantum together. So this package, along with Cirq, brings quantum computing. Imagine the supercomputer and the TensorFlow, one of the best or the best ML framework together. Imagine what it can be done, or what it can do, or what you can do using this. This is the value which Google brings to you. And again, I'm not just saying it because I'm a Googler. I was using it before even joining Google. And finally, the question, how do you access quantum processors, right? How? It's free of cost. You do not need any installation. Obviously, you have to install something, but you don't need any installation on your computers. And it's going to be totally browser based, totally. No installation, no upgrades, nothing to be changed. You can use your computer or laptop, what you're using today, and use quantum computers for yourself. I'll show you today. That can be done. To access quantum computers, you can use, but there are other methods to use as well. You can have a local installation of Python and whatnot, but I would recommend you to use Google Colab. So Google Colab is a free cloud service, and I have done that in my machine learning book as well. The name of the book which I have written is Adopting TensorFlow for Real World AI. In that book, I have extensively used Google Colab to walk you through the machine learning process and to be able to deploy the machine learning models all on Google Colab. It's a development platform tool, more experimental tool. I'm going to show you that tool in a few minutes. If you are new to Python programming language, you can go to tinyurl.com/free machine learning. I repeat it one more time. tinyurl.com/free machine learning, one single word. And you can access the Python programs and the machine learning programs which can help you start towards quantum computer. Using Colab, you can write all these or utilize all these machine learning frameworks like Keras, TensorFlow, PyTorch, Caffe, OpenCV, and whatnot. But then TensorFlow has the quantum computing package. How you can access Colab is using https colab.research.google.com. That is the place where you can use and access quantum computing. Now, let's jump on and see how you can access quantum computing. So this is Colab, and how do you access that? Using your Gmail ID, go to colab.research.google.com. And if it is your first time, it'll ask you to do a little bit here and there, accept some conditions or whatever, and then you can launch it. Now, what you can also do is go to tinyurl.com free machine learning, and you would see a list of things which you can learn on your own. This is the link for my book. But then machine learning of R, if you want to learn Python, Power BI, TensorFlow 2.0, this is something which you can utilize today to get started on Python and TensorFlow. Coming back to quantum computing, if you are familiar with notebooks, Python notebooks, Jupyter notebooks, this is what it is. It's a Jupyter notebook, which is a development environment for Python available on Google. Google provides you a platform to, if you go to colab.research.google.com, click on runtime and see change runtime type. You can see GPUs and TPUs. GPU is graphical processing unit, and TPU is tensor processing unit, which is the processor for running TensorFlow machine learning framework. Now let's quickly get started. So you are writing a quantum code. Can you imagine? Probably 30, 40 minutes ago, you did not know quantum computing, and here you are looking at a quantum code fast. You have to use pip install q TensorFlow -quantum. That is the name of the package. The TFQ is TensorFlow quantum package. I have already done that, so I don't have to do it again. And I run this. This is a Python language, and I guess Python is out of scope of this webinar, or teaching you Python is out of scope of this webinar. So import TensorFlow as TF, import TensorFlow underscore quantum as TFQ. TFQ is an alias for this imported TensorFlow underscore quantum library. Import circ, remember the framework, and SymPy, which is a Python library for symbolic mathematics. Run this and it's going to import. I've just written this print, putting into quantum computing and imported quantum. Boom. Whatever you write from here on would be quantum computing. I have a video series where you can see quantum computing, and I'm going to show you how you can access that. This is the basic quantum code of TensorFlow, where you see these are qubits, quantum bits, zeros and one together. These are gates. This is Rx and Ry gates, and this is your measurement. Remember the quantum diagram, the quantum circuit? This is a quantum circuit for you. This is, again, the basic hello world kind of a program, but this is quantum computing for you. If you want to learn more on quantum computing, you can type what is quantum computing and do it yourself, or DIY, do it yourself. The first video here in the videos section, you can look at quantum computer, or give me 1 second here. So I have my channel here. This is just a YouTube channel, and in the playlist, you would see quantum computing. So there are videos on quantum computing, which I keep on putting, and there are other videos on TensorFlow. So feel free and let me know if you have more questions. Julian, I'm done with my presentation.
Thank you so much, Naresh. It was like altogether a different sphere that at least I was in. Initially, it was like, okay, I'm trying to understand, I'm getting something, but somehow I lost in the track. But I'm pretty sure that others who are technically very sound, they have. Okay, I see one question. Hi, Naresh. What's the significance of the number 54? We are conditioned to think in powers of 2, 8, 16, 32, 64, etc. Just curious.
Yeah, so there are, if you look at IBM's computer, they have 50-bit qubits. So it's not any more classical computing. And that is the problem. At some point in time, when you're doing quantum computing, and it took time for me as well, I did it a couple of years ago. It took time for me to get out of that 2 raised to power thing. So you, in going forward in the quantum world, you will have 1 qubits, 2 qubits, and any number, 54, 72, and so on and so forth. So I understand your pain, but that is a pain you have to go through because you started on classical bits.
Yeah. Does it answer your question, Edwin?
Thank you, Naresh. Yeah, that really answers my question. I mean, it's just curious, so I'm new to this
Yeah,
whole.
it's a little bit different preposition, and you probably have to adjust to it. It'll take time. I never have seen a circuit like this before in my TensorFlow even experience. This is like a circuit. It looks like a transistor circuit. So it is what it is, right? I mean, you have to go through that process.
It's an awesome presentation. I really enjoyed it. Just had another question. So, I'm from the classical world many years ago. So you do have the classical gate configuration with using arsenic, phosphorus, and antimony for. But so I get to assume that somehow in quantum computing you don't do that. You just use the superconducting conductivity to handle this transient way of handling the gates. Is this
Yeah,
assumption correct?
that is correct. So this is where this is a very good point. I did not want to touch that because it gets a little complicated. But when you talk about 8086 microprocessors, or even those microprocessors which you and I have learned in our engineering days, those transient controlling is done through quantum energies now. So rather than, I mean, it's the same thing, right? Qubits can be either 0 or 1, and both at the same time. But it cannot be anything else, right? It can be 0 or 1. So the control of that circuit, the gate, the logical instructions, rather than being a transistor, here it's superconductors with quantum finite amount of energy. I know it's a little bit different, in fact, entirely different, but you will come to know about it very soon.
Awesome, thank you. I just wanted to understand that. So one more follow-up question because it's really interesting. So traditionally, the problem used to be that with using superconductivity, the amount of energy required to keep it cooled at absolute zero, was not beneficial to have a, it was not outweighing the need
The,
for having that. Have we crossed the bridge on that aspect of it? Is it safe to assume that way, or what's your take on that?
I would say we are on the bridge. So we are still not crossed there. We are not on the primitive side as well. We are at a level where we are on top of the bridge, understanding where do we need to go. So uh, to answer your question, think about this, and I keep saying this to a lot of my friends who know me. In 2008, 9, and 10, I used to do a lot of statistical analytics. There was SAS, if you remember. We did not know in 2008, 9, 10 that we are doing something known as machine learning 10 years later or 8 years later. Today, we do not know that what we are creating is going to lead us where. If you really look at it, quantum computing, the concept existed some hundreds or 50 years ago, but then, as you said, the cost benefit analysis is taking shape now. And I'm not just making it up, but using the quantum processing power itself, they are able to develop metals and materials composition, which can help them to build even powerful superconducting elements. And that is how 54, 72, 50, you will hear 35, those are not relation to 2 raised to power of, or multiples of 2.
Thank you, Naresh. Appreciate it.
Okay.
Thank you, Naresh, for a very interesting talk. At the base level, we understand quantum computing is an order of the magnitude improved speedy computer. Am I right?
Yeah, 2 raised to the power. Yeah.
2 raised to the power. And the talk was very interesting. I used a word building blocks. And that is what we got in this talk of yours as to the components that are going into it down to the coding level. Now, even among the computing community, when you see the code displayed on the screen, many people think it is Greek and Latin to me, I need a coder. But then you are able to explain what is lying in each one of the lines of code and what it means. So even for backbenchers and slow developers like me, it gives the confidence that we will be able to grapple with this, grasp this, and come to terms with this one day.
Absolutely.
So
And think
thank you
about
very
this.
much.
Thanks, Lal. Think about this, right? All this coding is ultimately going to be diminished to a level where even quantum computing would be a drag and drop.
Yeah.
So you will be able to pick up something, drop, and the quantum diagram will be created. But
Oh, yeah.
I don't think so we are there yet.
Yeah, it was very good, and you were hand-holding us and walking us through the various aspects of this technology. And it is going to be wonderful. And we will find pretty soon commonplace and day-to-day applications. With this kind of a speed, we may be able to declare the national election results in a matter of hours instead of days. Am I right?
Absolutely. Seconds, maybe.
Seconds, maybe we will be able to get in the elections, provided that it was not rigged. Okay. So it's quite exciting. The coming decades are going to be awesome and scintillating in terms of the speed and application potential of these new technologies. Okay, definitely coronavirus and any other molecules that you are trying to work through and see their efficacy under various conditions, namely the clinical trials, we can speed it up. Am I right?
Absolutely.
Thank you.
Thank you, Raj, for tying up election, quantum, and corona. So, yeah, what next? Any other questions?
All right, then. Thank you, everybody. I really appreciate it. I know it can be confusing, but you have to take that and learn from it.
Thank you very much.
Yeah, no, I'm absolutely, yeah, thank you so much, Naresh. It's just, those of us who had no connection and no, even thought process working. So lovely to have those areas opened in our minds. So thank you so much for this presentation. And yeah, if we don't have any questions further, then we'll end this session. But we do these webinars every Tuesday, Wednesday, Thursday, work and life webinars, professional webinars. But on Fridays, we have this Let Us Talk It youth series, which we have started a couple of weeks back, and it's just roaring. And tomorrow we have this session about phone hack, how the teens are unlocking themselves from their phone addiction. As far as phone addiction, it means a screen addiction, I would say. It engulfs everything related to screen and gadgets. So it will be, the teens have worked hard. So please be there to encourage them, get your questions out as much as you can, involve the kids at your home, and so that we can do the best what we can for the kids with the kids. So thank you so much all for joining in. And if you want to be part of the Let Us Talk It youth series, please do email us at webinar@letustalkit.com. And if you want to be a guest speaker, please, you can email us that too. So thank you all. Thank you, Naresh, once again.
Thank you.
Thank you, Naresh.
Thank you, guys. Bye.
Thank you.